Hello, my name is Prabha Khankar. I'm a production engineer at Mentor Graphics. I'll be talking about probing UPF dynamic objects, methodologies to build your custom low power verification platform. This is a short presentation. At the beginning, we will be talking about the outline and contribution of this research. This paper proposes a completely new low power verification methodology based on key concept of low power, which is actually UPF. We call UPF information model, which allows you to query any dynamic properties of UPF objects, like continuously probing on-off status of a power domain through Tcl API and pass the object information on the appropriately instantiated SystemVerilog API-based design codes. A Tcl API can be used on the simulation execution fly to populate any attributes of low-power SystemVerilog checker models that are already queried and bound during elaboration step onto RTL design through bind checker. It's true that we have used a lot of new terminologies in the previous slide, so let's explain those terminologies here. You might already know what is an UPF. Stands for Unified Power Format, which is an IEEE 1801 standard. So we'll not confine it only within the power spec of a language. It's a full command set or instruction set for verification, architecting, and implementing low power artifact onto any design. On the right hand side, we shows an example of a design which confined design top, CPU top, and other, for example, ALU top. And portion of this design are confined in different power domain, for example, top PD, sub 1, sub 2, sub 3 PD, and so on. Then we come, what is UPF information model? In the right hand side below diagram, we see that UPF and design HDL are combined to create a database which we call UPF information model that can be queried with HDL and Tcl API. We have used bind checker many times in this paper. It's a mechanism of custom low power checker done by embedding binding of design and checker within a Tcl file. That provides a consolidated verification, messaging, and debug environment. Simulator can access all instances of a target design with a custom checker. So what is the difference between a custom checker and SystemVerilog assertion? They can be very similar, but they can access the UPF object, which SystemVerilog assertion cannot. And you can also query Tcl or HDL native API with this bind checker. So what are the achievements and results of this paper? We propose a complete user perception that allows to query UPF information model database on a simulation fly and populate any attribute of user low power SystemVerilog checker modules that are bound in elaboration step into RTL design through UPF bind checker. This table shows the different phases of UPF information model processing that we confined a single UPF file flow that confined also the execution and elaboration and compilation of the design. The bottom of this diagram shows that SystemVerilog checker, which actually confined with a module and module. You can also insert properties and assert properties within this module and end module, just like a regular SystemVerilog checker. Only the difference is the ports are assigned to UPF HDL native class ID function. For example, UPF expression T, which is assigned to save condition or restore condition, and then you can use the save condition and restore condition to find the current value and fire the assertion on the execution of the clock. This slide shows further achievements and results through a consolidated UPF file, where the top part shows the regular UPF, the middle shows the binding of a design through bind checker, just defined in the previous slide. The checker retention model, which is bind to the TB, the top design, and the bottom part shows the utilization of UPF Tcl query function in a consolidated UPF flow. As a result, as we have explained, compile, optimize, and execution of simulation happens in a single iteration. So these results are represented here. We can see the save success or restore success or not success, and we can immediately load the debugger with the results of this information and identify whether these save condition, retention condition are passing or not, why they are passing or not, and we can also bring up the wave window to debug further to understand the current status or current value of each of these conditions. The concluding remarks for this presentation: we propose a methodology that allows to create low power checker. User can readily utilize object passing by query function, hierarchical references, as well with or without native SVHD representation. We identified some anomalies that need UPF LRM attention, which is broadly related to UPF generics like UPF generic clock, UPF generic data, specifically used in the record field of retention. We also conclude that we propose and implemented a novel methodology that paved the way to continuously probe UPF dynamic object and allows us to build a custom low power verification portfolio on existing low power simulation platform. Just like we build a retention verification checker, we can also build isolation, power switch, or anything that you want to build. So if carefully designed, this custom checker can be reused across any low power objects. With these I conclude. So if you have any question, let's start the question session. Thank you.